Alright, in this video I explain how to proceed with competitive inhibition, specifically how to derive the rate law for competitive inhibition. So we depart from the standard Michaelis-Menten kinetics mechanism, which is this one where these rate constants are k sub b, this is k sub a, and this is k sub a prime. And then we recognize that competitive inhibition is that in which the inhibitor competes with the substrate for the active site of the enzyme, of the free enzyme. Okay, so that is the free enzyme. This is where the inhibitor is going to bind. Okay, and we characterize this binding with the dissociation constant of this enzyme inhibitor complex, which has this value k sub I, dk, that's an equilibrium constant, is going to be equal to the concentration of free enzyme inhibitor over the concentration of the complex. Alright, so this is our reaction mechanism. Now what we want to do here is derive the rate law for it. Well, the rate of product formation, we can write it down right away, is just simply going to be k sub b times concentration of ES. Alright, it's just the rate of this last step. That's the only one that is producing products. Now, this is an intermediate, and you cannot leave it in the rate law, so the question is, well, how are we going to get rid of that and put it as a function of the concentration of substrate, the concentration of inhibitor, maybe this k sub I, and so forth. Well, what we're going to start with is with the mass balance of the enzyme. Okay, so at the start of the reaction, before any substrate or inhibitor have bound, the concentration of enzyme that you have is something that is set, that's a constant. This is the concentration of an enzyme at time 0. Now, once the reaction has started, that enzyme can be distributed in many different places. You can actually have free enzyme, okay, so that will be is this concentration of enzyme. Then you can have that the enzyme is bound to the substrate, okay, concentration of ES, and then you can have that the enzyme is also sequestered here with the inhibitor in the enzyme inhibitor complex, E sub I. Alright, so this is what we call the mass balance equation of the enzyme. Okay, mass balance. And it's from this expression that we're going to find out what ES is. Right, so that is a constant, so that's fine, but somehow we're going to have to put this as a function of ES, and sometimes we're going to have to put that also as a function of ES, so that everything depends on ES, and then you solve for it, and in the end you just plug it right here and find what the rate law is. Right, so let's see how we're going to proceed. Again, this is the constant, you don't have to worry about it. This is already as a function of ES. The question is, how do we put this function of ES, and how do we put that as a function of ES? Right, so our strategy for this, to put that as a function of ES, is to apply the steady state approximation for ES. Alright, from that equation, we're going to be able to find an expression that relates the concentration of enzyme to ES. And then from here, to be able to put that as a function of ES, we're going to have to use our k sub I expression. And we'll see how all that works out. Okay, so let's go in parts. Let's first try to see how applying the steady state approximation for the ES complex, we're going to be able to find the concentration of enzyme as a function of ES. Right, so let's think about the steady state approximation for ES. The steady state says that the rate of processes that are forming ES has to be identical to the rate of processes that are removing ES. Okay, so that the concentration of ES doesn't change in time. That's when ES reaches steady state. Okay, so well, what are the rates of the reactions that form ES? Well, there's actually only one reaction that forms ES, and that is K sub A. Okay, concentration of E and concentration of S. Okay, that is the rate law for the only reaction that forms ES, which is that one. Now, there's two processes that remove ES from solution. ES can react and go to products with rate constant Kb, okay, ES, and then ES can also fall back into reagents through rate constant Ka prime, concentration of ES. Right, so here we actually have again a way to figure out what the concentration of enzyme is as a function of ES, which is what we wanted to do. Right, so let's try to do that. Let's try to solve here for the concentration of E. And the concentration of E is going to be equal to K sub B plus K sub A prime, common factor of ES. Okay, that's what we have at the right-hand side of the equation. And then on the left-hand side, we're going to have here a K sub A times concentration of substrate. Okay? Now, this bunch of constants right here is something that should be very familiar. That is just the Michaelis-Menten constant. So we can actually rewrite this simply as K sub M concentration of ES over concentration of S. Okay? Alright, so we actually have already found what the concentration of enzyme is, that we actually have to put it right there. Okay, we're gonna keep this separated, like down here. Concentration of E is equal to K sub M concentration of ES over concentration of substrate, because we're gonna be using it later. Okay, we're gonna have to plug it right there after we're done with the other step. Alright, so that's the steady state approximation for ES to find the concentration of enzyme. Alright, so we have this piece of the puzzle solved, then we have to worry about that one. Well, this one we're going to get from the dissociation constant of this enzyme inhibitor complex. Okay, if you think about this expression, you can actually find an expression for EI, right? So EI is simply going to be equal to concentration of E, enzyme, concentration of inhibitor, over the concentration over the Egerian constant, or the dissociation constant of the complex. Okay, so that's fine. Notice though that proceeding this way, you still have this concentration of enzyme right there, which is not convenient. You would like to have that as a function of ES, but that's actually what we have already done in the prior step when we're trying to look for that one. Okay, so we can actually use that expression, put it right here as a to figure out what the concentration of enzyme is, and then we'll be set, right? So this is simply going to be equal to K sub M, concentration of ES, over concentration of S, concentration of I, over K sub I. Okay? So that is now our expression for EI that we're going to be plugging here into our mass balance equation together with the concentration of E, and then we'll have an equation that will look pretty long, but it will not be difficult to operate with. Okay, so let's do that again. The next step is just to plug this expression right there, and then that expression right here. Alright, so let's do that. Alright, so following here with the mass balance of the enzyme, we have that the concentration of E at time 0 is going to be equal to the concentration of E, which is simply K sub M, concentration of ES over concentration of S, plus E sub S, or ES, plus that, which we just have said that this was equal to K sub M, concentration of S, concentration of I over K sub I, and then concentration of ES. Okay, so that is the expression. Now we have E sub S as a function of simply constants, or things that we want in the rate law. Right? That's a constant, that's just fine. That's another constant. These we want in the rate law, concentration of substrate. That's another constant, that's another constant, and these we want in the rate law. We want to know how the rate is affected by any concentration of inhibitor. So we actually now are ready to proceed here, solve all of these for ES, so that we can plug it into the rate law expression and then find what the rate law is. All right, so let's see how we operate here. Now notice that these two terms actually have a common factor, Km over S. Okay, so that's the first thing that I'm going to do. I'm going to group them together and take common factor. Okay, so E naught is going to be equal, first I'm going to write that term, concentration of ES, and then I'm going to write these two factors, taking common factor Km S and concentration of ES. Alright, so concentration of ES, and then Km over concentration of S. Okay, and that is going to be a common factor of, well, that's just 1. Plus, when I take common factor of this, that is just going to be I concentration of K sub I. Okay? And we're actually going to call all of these parentheses, we're simply going to call this alpha to make things much simpler. Okay, this 1 plus concentration of inhibitor over K sub I is going to be a constant alpha. Okay? Alright, so then we actually have two terms right here that depend on the concentration of ES. We're going to take common factor and we will be able to solve for ES. Okay, so E naught times 0 is going to be equal to concentration of ES. Okay, that is just going to be equal to 1 plus K sub m, concentration of S, alpha. Okay, and now we're actually ready to solve for the concentration of ES. Alright, so the concentration of ES is going to be equal to the concentration of E at time 0 over that stuff, which I'm going to rearrange. I'm just going to write this first and then plus 1, just for convenience. K sub m over concentration of S, alpha plus 1. Right, so this is already the solution for ES, which now we could actually plug it right here and then proceed to find the rate law. But I'm actually going to simplify this so that it has an appearance that is very familiar to other rate laws that we have written. What I'm going to do is I'm going to multiply here and there by the concentration of substrate. And again, that is going to give this expression a very familiar look. Right, so there's going to be concentration of E at time 0 times concentration of substrate over Km alpha plus concentration of substrate. Alright, and this is something that is going to be much easier to write here into the rate law to find out what that rate law is. Okay, so I'm just going to erase the mass balance equation of the enzyme and all this to make room. Okay, but that's what we actually have used to find what the concentration of ES is. Alright, we just proceed with this and say that, well, rate is going to be equal to K sub B times that stuff, okay, which is concentration of E at time 0 times concentration of S over K sub M alpha plus concentration of S. Okay? Noticing that that is simply Vmax, we can write here the final expression for the rate law. Vmax concentration of S over K sub M alpha plus concentration of S. Okay, and this is the rate law for competitive inhibition. Okay, notice that it's not very different from how the rate law for uninhibited mechanism in enzymatic catalysis is. The only difference is this alpha. Right there in the denominator. That, remember that alpha is going to be 1 plus concentration of I over K sub I. Okay. Notice that if there's no inhibitor at all, if this concentration of I is equal to 0, then this alpha, all this term is equal to 1. And then you recover exactly the same law as when you don't have an inhibitor, which makes sense. But as soon as this is a little bit larger than 0, what that's going to mean is that this alpha is going to be a little larger than 1. Okay, and if this is a little larger than 1, what that means is that the denominator is a little bit larger than the numerator. So then what happens is that when you have some inhibitor at all, okay, this rate is going to be lower than the rate when there's no inhibitor, and that's what slows down the rate. Okay, why the rate, once you have a competitive inhibitor, becomes slower. Okay, the reaction gets decelerated. Okay, anyway, so this is the derivation for the rate law for competitive inhibition.